Okie dokie, so it's been quite some time since we last did this. We went over since last, so we skipped a whole semester, and so since last semester was mostly math, there were some statics in there, which if I go over any statics, it's going to be in mechanicals of materials. Statics is pretty simple. There's no motion in statics. It's static. So going from there, the classes I'll be taking this semester are engineering dynamics. We'll shorten to Engine Die. Cause yeah, fun. And then MOM, which is mechanics of materials, obviously capital M's. And then Nuke, which is nuclear engineering 1. And then MEM, which is mechanics of engineering materials. And then DiffEQ, which is differential equations. This is the only math class this semester. The other math classes, I believe I did go and record some Calc 2 classes. So if you come across if what I'm saying is weird and you don't know what I'm saying, just give me a call. The people watching this probably know me personally. So to begin with dynamics. So dynamics is the opposite of statics. We're going to be using motion to find weights on particles, movements, bearings, things like that. So the gears, so the pressure on gears to make them turn, things like that is what we're going to be going over in engineering dynamics. To begin, engineering dynamics started off pretty simple. If you remember from Physics 1, Physics 1 was pretty simple because we had kinematics. So we had kinematics. This is just movement of bodies using Newton's laws, gravity, equal and opposite reactions, and things like that is what kinematics is. We will go over kinematics and kinetics, but right now we're just going to talk about kinematics. Sorry, kinetics will be later. Kinetics is going to be gears, things like that. There were two bodies we're going to talk about. So two bodies or ways or things we're going to apply the force on. The first one is going to be a particle, and the second one is going to be a rigid body. A particle being a very small thing, one that we're not going to take account into the body. So it's going to be just this dot that we say, oh, a force is applied on it this way, and this is the force, and we're not going to take into account to how big the particle is, what the particle is, its mass, anything like that. A rigid body, we are going to take into account the thing that we're pushing. So it's going to be like a block of wood. This is going to have its own weight, and it's going to have different things depending on where you push it. Like if you push it from the top, you might tip it over. If you push it from the bottom, you might get it to move. Things like that is what a rigid body is versus a particle. So to go over some of just what we've been doing with kinetics and engineering dynamics is we've been doing just the simple constant acceleration, constant velocity things. So just a couple equations that you need to know for constant velocity and constant acceleration. This will help you solve most particle problems in kinematics. So these are, so for constant velocity, you're going to have x0, and I'll explain the variables here in a second. X0 plus equals x plus v not v naught t. I need to check real quick. I believe it's v naught t, but it might be vt. Yes, it is vt. And then, so this is constant velocity, so const velocity, and then you're going to have constant acceleration, and that's going to be v equals v naught plus AT. And then you will have two more equations that are very important for helping with this. And the first one is going to be x equals x naught plus vt v naught t plus 1/2 at squared. And then the other one is going to be v squared equals v naught squared plus 2a times the change in x, or x 0 x minus x naught. This is the change in x, delta x. So x is displacement, how far you're moving. So like walked out of screen, I had to move 2 feet forward. That is your x. If you're dealing with up and down, then you can replace this with y. Very simple, just x and y. X is this plane, y is this plane, and so you just replace x with y in all of these equations, and it comes out very well. X0 is your starting position, t, obviously time, and v is your velocity. Most of the time, so there's two different v's that will represent v like this with an arrow above it is velocity, true velocity is what I'll call it. It's true velocity, it's a vector, you have magnitude and direction. So velocity is saying, oh, I'm going north at 70 miles an hour. That is true velocity versus just saying I'm going 70 miles an hour. That's going to be called speed, but speed will be represented with v. When we get into any math that's actually involving the velocities, I'll go over what it looks like, your x and your y and your z-axis, stuff like that. But that's a very big thing. So then A here is acceleration, and that's the same in all of these equations. V0 is your starting velocity. So you notice that these two here, they're finding similar things. This second one is independent of time. So if you don't know your time and you know your starting velocity and your ending velocity, and you want your acceleration or you want your change in where you end up, but you don't know your time, this is your best bet. This equation here. This one is going to be dependent on time. So you know your car travels for 40 seconds, and you know its starting velocity is x. So then you're going to use this one. You're just going to use these equations for most things. Pretty simple stuff. Delta x will always represent a change in x. That's always what delta means. And then constant acceleration just means that you're accelerating at the same pace the entire time. Your acceleration never changes. Same for constant velocity. And velocity is the derivative of displacement or distance. So it's the derivative of distance, which will be written as dx over dt. So this is the derivative of displacement x, which is equal to v, or represented by x dot. And then the acceleration is the derivative of velocity, which is dv dt, which is acceleration, or x double dot. This dv dt can also be written as d squared x over dt squared, which just means that you take the derivative twice of your displacement. That's all it is. Very simple, very basic-ish, kind of. If you don't know how to take a derivative, it's not that basic, but as long as you know how to take a derivative, finding your velocity or finding your position from velocity is going to be the opposite, which is an antiderivative, or taking the integral. That's pretty simple, and what we're dealing with here. Dynamics also deals with, we're probably going to be doing a lot of cables. So an example of the cable, because it's easier to just show an example of a cable and explain how one might go about solving this or doing it. So you have an elevator. This is an elevator. I will represent it with E, obviously. You're going to have the roof here. It's going to have a pulley. It's going to be attached to this counterweight. This is going to be the winch. It's going to come up, go around, just a sec. I need to make sure. Yes, it was correct. Okay, it was correct. So you're going to go up and around and around and up. This is going to be not a W. We're going to make it pulley, P-U. And then we're going to call this height to here, Y of C, this height to here, Y of E, the distance of the elevator, and this height to here, Y of W. So here you go, you have your elevator. You're given the velocity of the elevator, VE, is equal to 2 meters per second. Down is positive, so our elevator is going down, so people got in, and they're going to the first floor from the top floor. And so positive direction is down. This is your coordinate system. Always define your coordinate system, so when you're conveying it to other people, they know that left is positive and right is negative, so that they know what you're doing. So down is positive. Our elevator is traveling down. The question is, how fast is the counterweight traveling, and which direction? So the question is, okay, well, how do you go about this? It's very simple once you see it. So you have distances, right? And you have a velocity. So velocity is the derivative of distance. So, okay, so what are your distances here? Well, this distance is Y of E. It's the distance of the elevator. And this rope is never going to change how long it is. It's impossible for this rope to magically grow in distance or decrease in distance. And this here is Y of W. This length is Y of W. And so you have Y of W and Y of E is going to equal a constant length. They are going to equal the length of this entire rope. So Y of E plus Y of W is equal to constant. And constants will always be represented by C. If there's multiple we'll just put numbers, subscripts in front of them and go from there. So the derivative of placement is velocity. So we're just going to take the derivative of this entire thing. You can take the derivative of this and the derivative of this, and you'll get VE plus VW is equal to, constant derivative is 0. So VE plus VW is 0. So to solve this question, you will subtract VE over, and VW will be negative VE, which is negative 2 meters per second, which means that W is traveling up. So the displacement on W is negative up, or negative up, yeah, that's what you would say. Same thing over here, except this time there's going to be, if you want to know how fast the winch is pulling, then you would say, oh, okay, so how fast is this winch pulling? Well, we have 1 YC right here, 2 YE, because these are attached to the elevator, and it's going to be, oh, okay, so we have 2 YE here. Y is going to travel upwards, and the elevator is going to travel downwards, and so these are going to be traveling upwards. And so it'll be 2 YE plus 1yc is equal to a constant again. This rope never changes its length. And then we'll have 2ve is plus vc is equal to 0. So you'll subtract 2ve over, and vc, the velocity of this, is equal to -4. If you want to know its relative velocity to something else, you will take, so the relative velocity of point C to the elevator, you will take VE or VC minus, it's VC over VE, which is equal to VC minus VE, which will be -6 meters per second. So if you're on the elevator and you can see out, this cable will be going by you at 6 meters per second. That's all it is. That's engineering dynamics. We will talk about next time for engineering dynamics. I'm already at 15 minutes, and I'll try to make each subject 15 minutes long. So next time we will talk about rectilinear motion, or curvilinear motion. Rectilinear motion is just on lines; it makes rectangles. Curvilinear motion is curves, but your rigid body stays oriented the entire time. It stays correctly oriented. So it's got these 2 points, A, B, A, B, A prime just means that it's moved, same A though, B prime. So this is rectilinear, you travel straight along like you're going on a rectangle. And then curvilinear is like this. A prime, B prime. It's no longer straight. You're taking dips or doing some weird things, but the orientation of your object never changed. Okay? That's what we will talk about next time for engineering dynamics. And it's going to get a lot more complicated because next time we're going to be taking derivatives and integrals and things like that of lines. And so hopefully you know how to do that. Hopefully. So now we're going to talk about mechanical mom. I forgot what it was called. It just left my mind. This is statics plus, I guess is the way I would put it. It's kind of very difficult. So we're going to talk about shear and stress, and then the stress shear diagram of materials, because that's what it is. It's mechanics of materials. And so stress and shear. So stress, shear, and they have defined stress to be wonderful. It's got limits. So stress is going to be represented by sigma, lowercase sigma of Greek letters. So stress will be represented by sigma. This is sigma. And shear is going to be represented by tau, which looks like this. So sigma and tau, stress and shear. Technically they're both stress, but this is normal stress and this is shear stress. Different. So shear or normal stress is going to be defined as the limit. It's internal mostly. So shearing has to do with so you have two boards like this, and you put a pressure going this way on them, and they snap like that. That's shearing. Stress is you have two boards like this that are intertwined together, and you pull them apart, and they start to loosen. That's stress. So stress and shear in some manner. But stress is defined mathematically as the pressure over the cross-sectional area. So the pressure over the cross-sectional area, it's how much force per meter squared is pressure. Newton over meter squared is pressure, or pascals, which is pressure. And cross-sectional area is the diameter. So this is your cross-sectional area. If it was a square, it's length times length. And shear is defined as V over A. V is just what we represent as shear pressure. It's different than total pressure because you're going to have an object, and here's your pressure, here's your P, and you look at this area here, well, you're going to have just a normal stress in this area, and it's going to be, this is fixed. We'll make this fixed so that makes sense. So this is fixed, it's not moving, but it's just got a ton of pressure pulling on this way, and it's pressure and pressure and pressure. And so this area, it's three-dimensional. This area is your cross section. This is A. Okay, so this is stress. Now let's say we put some bolts in it. So we put a metal pipe or a metal sheet here, and then run a bolt in it, and then move P, which is P total, up to this plate, like this. Now this bolt is going to be in between, so it's going to be in between these two places. So here's the sheet, and here's the wood, and the bolt runs into it this way, and then into it here. So it runs into both the wood and the sheet and the sheet metal. So you're going to have 1V here, the top, 1V here, beneath, so where they're connected, that's going to be 1V as well. And then since it's two different materials, you'll have another V, this will be two V's, so one for the top, where the metal meets, and then one for where the wood meets the metal. So metal meeting wood, wood meeting metal. Those are going to be two shears, so two V's. And then this third one, or fourth one, is going to have another V when it actually goes into the wood. And that's going to be your shear stress. So here, stress is going to just equal PA, which will be this whole cross section, adding the wood. And then your shear stress is going to equal 4VA, where 4V is equal to P. So the bolt is more likely to fail than the internal components because it actually has higher shear stress than it does normal stress. Yeah. If that should make some semblance of sense. It's pretty difficult actually, but that's normal in shear stress. Solving problems using these is relatively simple, and by relatively simple I mean it depending on how many structures you're wanting. Like if you involve trusses, it sucks toes, and so forth. But that is normal stress and shear stress. And then we will continue on to strain. Strain. Okay, strain. There's some other things that we talked about, such as like designing for shear stress and normal stress. It's like allowable ASD, allowable stress design, is how like they're like, oh well, wood fails at 20 kips, 20,000 pounds per square inch. So we're only going to allow 10,000 pounds per square inch to be put on here. That's allowable stress design. So you design it as if it would fail at 10,000, or 10,000 is the max that it can take, and that's how you would design it. That involves the design process. So strain is the measurement. Finally we have some words. So now we have words. Strain, measurement of deformation. That is strain. It's the measurement of deformation due to an external load. So something's pulling on this marker, and it stretches some amount. So there's this diagram that is very, very helpful. It's called the stress-strain diagram. Stress-strain diagram. It looks something like this. And it's got 4 regions. This first region is the elastic. This is the yielding. This is fracturing, necking. And no, I have not. That's just what it's called. Funny joke there. Ha ha ha, necking. Ha. And then this is strain hardening. Okay. There's a couple very important points. In this area, in the elastic region, this slope here is known as E. And E is when the stress, so this is stress, so right, represented with sigma, and this is represented with epsilon, and it is the strain, so the deformation of the material that we're measuring. So this is going to be increments of meters, so it's like Laffy Taffy, and it's like, and you can really strain this puppy out. Laffy Taffy is a pretty poor example for the elastic region, but whatever. So first off is the elastic region, and the elastic region, anything in here. So you're straining the material. You're putting a pull on it, some external load, and it's deforming. You can visibly see it deform. It's getting longer and longer, so you're pulling on it, so it's intentional. It's getting longer and longer. Anything in this point until this little thing right here, until the proportional limit, it will go back to its original length. So you're pulling on it, pulling on it, pulling on it. It's going up. It's getting longer and longer as the stress gets higher and higher. It's getting longer and longer and longer. And then right here, you stop putting stress on it. So it stops. So it stops increasing your stress. You put 1,000 kips on it. And then you take the 1,000 kips off. It will go back to its original length. It won't have increased at all. Nothing bad will have happened. Once you pass this proportional limit, then it no longer will go back to its original length. So you have this material, and you're going along, and you keep putting stress on it, and finally you're in the yielding. So the yielding means that the stress isn't increasing at all. So you have not increased the stress, but it's still straining, so it's still gaining length, okay? And this is called the yielding region. If in the yielding region you remove the stress, so you're like, oh shucks, I went too hard and I'm now in the yielding region, what's gonna happen is it's going to decrease, it's going to shorten. You didn't totally ruin your material. I mean, it's ruined, but you didn't totally ruin it. It's no longer broken. It's not broken. It's going to decrease, but not back to the original. So you stop here. You remove the stress. It's going to follow this this proportional, this E. It's the slope of the proportional time, the proportional elastic region, and E, elastic slope is what it's called. So you stop. It's going to follow this E back to some length, but it will not be its original length. So that is the yielding region. Once you get to the strain hardening region, the strain's going to increase again. So you're putting more strain on it, so the strain increases again, and it's going to look like your material is perfectly fine. It's going to take a ton more strain, like a lot more strain, and it's going to be, you're going to see a little more deformation on it, but it's not anything like crazy, just regular increases. And finally, you're going to get to this limit right before necking, and this limit here is called the ultimate load. So it's the ultimate load. It's the max amount of load something can sustain before it starts to break. Okay, so like steel is like 26,000 kips or 26,000 pounds per square inch, something crazy, before you actually start seeing it necking. So necking is you hit the ultimate load, and now the strain is decreasing. So you bottled off. You're collapsing, and so the material is this big originally, and you're going, and now you're seeing deformation, like actual really bad deformation. The cross-sectional area is getting smaller. In none of these has the cross-sectional area really changed that much, but now the cross-sectional area of your object is changing a ton, until it gets to this point in which this is fractured, it snaps, it breaks apart. And so this is your stress strain diagram of materials, your strain, your stress, how much you're applying on it, and so forth. This underneath the curve, so all of this underneath the curve, this entire area here, is known as the toughness of the material. This entire area is known as its toughness, how much it can strain before breaking. the modulus of resilience is important because the modulus of resilience is a area of toughness, but it's this area underneath the proportional limit. The modulus of resilience is when, so it's when you're underneath the proportional limit, so how much stress it can sustain while maintaining its original shape. That is the modulus of resilience. The modulus of toughness is this entire thing, how much it can sustain before it breaks. Simple, straightforward. That's about it. If you're looking for the actual load, so if this had actual measurements, the actual ultimate load would be found by finding your sigma u, so your sigma ultimate, and then multiplying it by that cross-sectional area. That's how you would find your ultimate load or your proportional limit. That's just how you would find those things. It's just the cross-sectional area times the stress at that point. And that's how you would go about it. That's what we've been doing in mechanics of materials. Simple, straightforward, kind of cool, kind of interesting. We will be talking about some brittle materials and ductile materials. This slope is only, or this stress strain diagram is only of ductile materials. Like a brittle material, kind of how I understand it so far is a brittle material might strain a little bit, like a tiny bit, and then once you hit this proportional limit, like a brittle material's slope of this E is going to be like 1. It's going to be like a straight line. So you're going to be like, maybe see a tiny bit of deformation, and then it's just going to snap. Well, ductile materials will start to bend or elongate or something. But steel is pretty much just a straight line, even though it's a ductile material, so yeah, interesting. So nuclear engineering is next. Nuclear engineering, super simple stuff we've been going over in nuclear engineering, like basic chemistry, things like moles, Avogadro's number, really not big, heavy hitting stuff like the last two kind of were. Engineering dynamics was kind of like physics 1. Mechanics of materials was kind of like statics. There's some statics involved, but it was a lot more conceptual things before we actually got into like a bunch of math stuff. So I'll be going over some nuclear units, some stuff like that, just like the simple basic nuke stuff that we've been going over. So atoms, I'm going to grab my chart of nuclides book. I might not draw much up here, but this is the chart of nuclides and isotopes. It's a freaking cool book. It's got like nuclides and isotopes. It's pretty cool. But nuclear engineers will deal in our energy units are electron volts. So it's EV, electron volts. It's how much one electron gives off. It's the voltage of an electron, which is something over time, something over seconds, I forgot, is a watt, which is almost a volt. 1 electron volt, for perspective, is 1.602 times 10 to the negative 19th joules of energy, which is a tiny amount of energy, minuscule, barely recognizable. But we deal with atoms, and so we deal with electron volts because it's simple, easier to deal with than dealing with big power numbers that are really small or really big. I mean, we deal with really big power numbers anyways, but time for another thing, whatever. U-235, super cool. This is why nuclear engineering is freaking awesome. Gives off 200 million electron volts for one atom. So one fission, U-235, 200 million electron volts. This is enough energy to visibly move sand, one sand grain. And by visibly move, I mean like it moved. But that's from an atom, which is just freaking awesome, okay? So like one fission is enough to move one grain of sand, maybe 3 sand lengths, which is like so cool. Anyways, atoms are very important for nuclear engineering. We should go over them because refresher course. I'm looking for a bigger box that I can show you so that I can explain the atom, what it is, what's going on. Okay, here we go. Nope, you don't want indium. Cesium works. So, I'm not sure how well you can see that. Not very well. Okay, I guess I'll just draw it then. So, we have an atom. I was hoping that would work so I don't have to draw this, but whatever. So we have an atom. You're looking at the periodic table of elements. It's got the element name, which is represented by something I forgot. So we'll just say we got some sodium, because sodium's cool. We got the A number, not the A number, the Z number, the A number, and the Z number. Z is very simply, it's number of protons. It wasn't yet. The number of protons in the atom. So sodium has 11 protons. So the sodium Z number is 11. A is the number of protons and neutrons in the nucleus, which allows us to differ from nuclides or different isotopes, is the A number. The A number and the atomic mass of sodium are different. So they're very close. So let's pull up sodium real quick. So sodium, the A number is not its atomic weight, it's just the number of protons and neutrons it has. So sodium 23 has 11 protons and 12 neutrons. But its atomic weight, or its atomic mass, is 22.989. So it's not quite 23. And that's the difference there. Super easy, don't know what else to say. Atomic mass units, AMU, are based off carbon-12, so C12, which C12 weighs pretty much exactly 12 AMU. If you have 1 mole of any of these, any element, if you have a mole of any element, which is Avogadro's number, it is 6.022 times 10 to the 23rd items. Usually atoms or molecules or whatever, but you could use a mole and be like, dang, there's a mole of cars over there, but I don't even think there's a mole of cars yeah, it's not even close. You'd be like, dang, look at the sky, there's a mole of stars. Probably not, but pretty cool. This can be used anyway, it's called a mole. Like, yes, the underground creature that digs holes and was evil in G-Force. So the AMU is based off 1/12 of the carbon-12 atom, And so if you have a mole of any atom, it will weigh that in grams. So 1 mole of carbon-12 is 12 grams. 1 atom of carbon-12 is 12 AMUs. Pretty cool how that works. We reverse engineered it so it would work that way. That's why it works that way. Makes math way, way, way easier. You have no idea how much it's so helpful in any calculation dealing with atoms ever. It's wonderful. So then we have isotopes, which have the same Z number. So same protons, different neutrons. So it's the same element. That's just has different number of neutrons. A nuclide is anything with a different Z number and a different A number. So anything that has a different number of protons and a different number of neutrons, and only one of those conditions has to be fulfilled for it to be a nuclide. So it's got 1 proton and no neutrons. That's 1 nuclide. It's got 1 proton and 1 neutron. That's another nuclide. 1 proton, 2 neutrons. That's another nuclide, and so forth and so forth and so forth and so forth and so forth. And that's a nuclide. And then we went over isotope. Then we have isomers, which are kind of cool. They're the same Z and A number, so same protons and neutrons, that have different stability states. So you can't quite see that, but this is selenium 77, and it's got 2 little boxes here. One is naturally occurring, and the other is unstable. And so this other unstable one will throw off a bunch of gamma rays to become stable. That's kind of hard to see, but this is an isomer. This one right above it, bromine 79, is also an isomer. Okay, so it's got 2 different stabilities of the same atom. That's an isomer. Really, those are the only 3 important ones. The other ones are not that interesting. There's atom density, which is pretty simple. Number density is very important, so we'll go over number density. So number density is a little long. So it's the number of atoms in a given volume is number density. So you have a cup of water, and you know the volume of the water is 300 milliliters, which is 300 cubic centimeters. Maybe. So you want to know how many molecules of H2O are in 300 cubic centimeters of water. What you're going to do is it's this very simple equation: N equals rho NA over M, where rho is the density in grams per cubic centimeter, so rho equals density, and A is your Avogadro's number, so this is 6.022 times 10 to the 23rd atoms per mole, and A getting lazy. And then M is your atomic weight. So your atomic weight is going to be in grams per mole. And that's your number density. And then you can simply just plug all of these into this. So your density is grams per cubic centimeter. You look that up online. It changes for everything. So you find that, and then you put that in there, and then you find, Avogadro's number, you put that in there, and then you divide it by that, and you're like, oh wow, there's 4.02 times 10 to the 22nd atoms in this many cubic centimeters of water. Wow. And that's number density. It's important for some things later on. There's also weight density, which is totally different, because weight density is dependent on the weight of the atom and not like the number of atoms. So like water has 2 hydrogen, which are super light, 1 oxygen, which is stupid heavy. Not stupid heavy, just heavy. And so the weight density is like clearly just all oxygen, while the number density is mostly hydrogen. Simple, straightforward. There's isotopic abundance, which is just like, is it naturally occurring? How much of it is naturally occurring? You have 5 naturally occurring ones, and like, what's the percentage of the weight percentage? And then you're just gonna do some basic math and be like, well, this one has 0.5% of isotopic abundance, and it weighs this much, plus this one who is 70% and weighs this much, and plus this one who is 10% and weighs this much, and then you just add them together, super easy, barely an inconvenience. Now we have mechanics of engineering materials. This one we'll talk about for like 5 minutes probably, like not much. Not much to talk about. We're going back over atomic structure, some bonding forces, so it's bonding forces, like ionic, covalent. It's pretty basic from chemistry 1. The way things are produced is one way we're going to look at this. So we have performance, perform, and then properties, and then structural, and then processing, and then chemical. So you want it to perform in this way, so you want it to hold 5 million pounds of horseradish. So you need it to perform like that, so it can't corrode. Okay, so properties: can't corrode under horseradish, has to maintain strong whatever. You set the properties up. You say this and this and this, we need this and this. Then you find the structural, so like what kind of grains, what crystalline structure, what luster, things like this, where it's like structurally integral to the property. And then processing, like hot rolling, cold rolling, what kind of steel, are you going to twist it, are you going to kind of that. And then chemical, like what kind of chemicals are you using? Are you using aluminum, are you using iron, are you using nickel, cobalt? What are you using to get to this performance? And that's what we're going to be doing in mechanicals of engineering materials, is we're going to be looking at these and being like, okay, so how do we get from here to here? Because you start at the top and you work your way down. So how do we get from here to here, and what do we need? That's mostly what we've gone over. A bunch of other chemistry stuff like orbitals and things like that. But yeah, that's about it. So, like I said, that one was super easy, barely an inconvenience, and this next one is going to suck toes because it's super hard, very much an inconvenience. So this is differential equations, and everybody loves differential equations, and I'm lying to you because nobody likes differential equations. because it is a pain in the butt, literally. So to begin with, we just like went over like constant acceleration, velocity, stuff like that. And then we need to talk about orbitals, not order. So the order is of a differential equation is how high your derivative goes. Doesn't quite make sense. So you have a differential equation which looks like this. So you have so it's differential in y, so you have y triple prime plus px, which is a function of x, px, function of x, y double prime plus gx, y prime plus y equals 13x. This is a differential equation. Ta-da! I don't know how to solve it yet, because this is a triple. The order is 3, because this is the third derivative of y. Yeah, that's order. So if this one wasn't here, this would be a second order. Since this one here, it's a third order. That's what order is. Right now, we're solving first order differential equations, and they are very difficult, so I can't wait to get into higher order differential equations, which, like by the looks of it, are going to be even worse than first order. Because first order is written in the manner, there's homogeneous, not homogeneous. Homogeneous means it equals 0, not homogeneous means it doesn't equal 0. I'll show you how to solve both of those today. So first order differential equation looks like this. Y prime plus px y equals 0. This is looks, oh my goodness, this looks so easy. Like, I am not joking, that looks so easy. But I promise you, it is not. Oh, that's how to solve. Dum bum bum bum. Okay, first order differential equations. Yes, this is what it looks like. And you're like, that doesn't look too bad, Clint. Like, I don't know why you're like stalling and talking about this. I mean, technically, we first should talk about how to solve differential equations. If you're given like the solution to this differential equation is this. If you're given the solution to a differential equation and it's y equals this, and you have y prime and y, you just simply plug y in to y, and then take the derivative of y and plug y prime into y. Super easy, barely an inconvenience, super basic. It's just like solving a solution when you're given x. So you're given the solution where x equals 4, and you have x equals 4. You plug x into 4, and you say 4 equals 4, and you're like, wow, that's so simple. And that's how you, if you are given y, that is how you solve a differential equation if you're given y. If you're not given y and you're told to solve this differential equation, here is what you do. So you have y prime and px of y equals 0. So first things first, you subtract the pxy over. So y prime is equal to negative px y. Okay, y prime is written dy dx, which is nice because you see this x here and this x here. You must get your variables together. This is called separable variable equations. It means you can separate the variables and get them together, and then you can take that integral. So you can take the single integral of these two variables that have been separated. So then you're going to divide the y over. So divide the y over to get it over on this side. So divide y. 1 over y. And then you're going to multiply by dx to get dx on this side. So then you'll have 1y times dx, 1y dy equals negative px dx. And this is a separable variable equation. So you have 1 over y on this side, dy, so this is solid integral, and you have negative px over dx on this side, which is another integral. And you're like, oh yeah, that's not too bad, and I would agree with you, because we're only dealing with a y and a px. When px is like 1 over ln of x plus 3, it sucks because you have to take the integral of that, because now you have to take the integral. You have to take the integral of this, and everybody knows, right, everybody knows that the integral of 1 over y is ln of y, the natural log of ln of y. Yeah, just some things you just memorize, okay? So, this will equal ln of the natural value of y is equal to negative p, capital P. This is where p of x is equal to the antiderivative of p of x dx. This is how we're going to write it. This is the fundamental something of calculus. The fundamental law of calculus, fundamental rule of calculus, something like that. Very important rule. Don't forget that one. So px is the integral of p of x, but this is capital P. Don't forget your negative. Of p of x plus c. Do not forget your c. We'll call this c1. And then what you're going to do is the opposite of ln is e. So you're going to take this to the power of e and this to the power of e. So to the power of e. So you will have the absolute value of y is equal to e negative capital P of x plus c1. So then this e can be separated out because this is the same as the natural log. This is the same as the natural log of y is equal to e negative px times e of c1, which, right, because you're multiplying, and when you multiply the same constant, you add the powers, so this is the same as this, math. And then e of c1 is obviously, can just be written back as c2, because this is just a constant. E of c1 is just a constant, and so we can make c1 whatever we want it to be, and so it doesn't matter, it's just another constant. So then we get the natural value, the absolute value of y is equal to c2 e of negative p of x. Now, to get rid of this natural value, that means it's plus or minus. So plus or minus y, that gets rid of the natural value, which equals plus or minus c2 e of negative p of x. And we're just going to put the plus or minus into c2 because it's a constant, and we can do whatever the flip we want with constants. And so it will be y is equal to c3 of e of negative capital P of x. This is usually how you solve a homogeneous means it's equal to 0, first order differential equation. Wonderful. So we have our answer to a first order differential equation. We will always call y1 is equal to e of negative p of x. We have made c, your constant, always equal to 1, and that we will always call that y1. Okay? Remember that, it's important. So y equals negative e, y equals e of negative p of x, that's y1. This is the solution for a homogeneous equation. For a non-homogeneous equation, so that means there's something on this other side. So you no longer have it equal to 0, you now want to know that this is equal to g of x. I may screw myself over in this by doing this, but we will find out. Is equal to g of x. So now you have g of x. So what do? First of all, you solve the homogeneous equation, which we just did. So we said y is equal to c of e of negative p of x. Okay, wonderful. We have solved this. So now, what do? That's a great question. Now, we say, okay, so we have to solve this differential equation here. So we're going to make y equal to u of x times y1. Remember, y1 is just, or c is equal to 1. So it's e of x times negative p of x. So to solve, we have to take the derivative, because we have to plug it into here. We're going to plug this u of x, y1 directly into here. Yes. I'm going to plug that directly into there. So, derivative of u of x, y1, derivative of y1, y is equal to u prime, I'm removing the x, is equal to u prime times y1 plus u times y1 prime. Okay, this is basic product rule from Calc 1, right? Calc 1. Sounds easy, it's not, because this is a differential equation. So then we're going to plug this into y prime. So you will have, you're going to plug this into your whole thing. So you will now have u prime of y1 plus u of y prime of 1 times, or plus, p of x times y, which is u of x times y prime. And now you're like, this will equal g of x. And this looks pretty gross, because it is pretty gross. It's hideous. But there's a massively helpful trick. So, if you recognize this here, y1 is this. U of x is what we're solving for. So u of x, y1 is the base value of y. Okay. P of x is this p of x right here. So this plus, so we're going to remove these brackets, plus u of y prime of 1 is this equation right here. It's your this is your homogeneous equation. And it's a little hard to see because, so you group this together and you're like, well, I don't know how I'm looking at the homogeneous equation. Here is how you're looking at the homogeneous equation. You ready? You factor out u. So you will have u times y prime of 1, so y prime of this, plus p of x times y1. And so you remove this 1, well, you have y prime plus p of x, y, and your homogeneous solution is equal to 0. So this right here is equal to 0, which means that this u times this is 0. So this all magically goes away. Magically. Super cool. Thankfully. Because if it didn't, I would probably cry. So this all goes away. And you're left with u prime times y1 is equal to g of x. That's pretty cool. Pretty neat. So u prime y1 is equal to g of x. Now what do? Well, very simple. You just solve an integral. So you get u by itself is equal to g of x divided by y1, and then you take the integral of both sides. Because what you do to one side, you must do the other. You take the integral, you get u is equal to the integral of g of x over y1 dx. And then this, you just plug back into here, into your y, because u is, we're solving for c. That was our whole point, was to solve for c, because c is dependent on some value of x. C is dependent on some value of x, and so we have to solve for this equation here. So then we're going to plug this back into y, and we will get the solution to get g of x of this. So we will get y equals the integral of g of x over y1 dx times, times e of negative p of x. This is your final solution. Of this integral here. This is technically the formula for it if you wanted to get like whatever it's called. And then to check, you take your answer, you take the derivative of your answer, and you plug the derivative of your answer into here, you plug y into here, and you see if it equals this g of x. That, ladies and gentlemen, and I mean people I know, is a differential equation. Homogeneous solution and non-homogeneous solution to solve. This is the simple way of showing it because I don't want to take any integrals today, because integrals freaking suck. Like this is what you have to do to take some integrals. If you see that, the integral of one thing is equal to u of x minus the integral of your other thing. This is called integration by parts, and it blows. And then there's u substitution, and don't even get me started on trigonomic substitution. It just integrals are the freaking worst. So next week we'll probably doing much higher order differential equations. I don't really know what we will be doing, but this class is very hard because math is very hard. So I wish you the best. I hope God does good things to you, and I pray that I may make it through the next 4 years. Merry Christmas.